amplitude modulation, frequency modulation, phase modulation. Basically what you do is you have a sinusoidal carrier and it has got three features: amplitude, frequency and phase, and you can change those or modulate those parameters instantaneously in accordance with the modulating signal, which will be your voice, video, whatever, and then you get what is known as modulated signal. And there could be three of them, and mix and match of all could be also possible. Various things people can do, particularly for digital modulation. There could be a large variety of such modulation schemes. So first of all, we should also appreciate that the needs of modulation and demodulation. Can anyone tell why do we modulate the signals carriers? Some of the students. Why modulation is required at all? You must have studied in analog communication systems.
Ravi is there in the class. Ravi, are you there? Praswal from section B. Please answer this question. Anybody else?
So, sir, we require modulation to increase the strength.
Increase the
strength of the message so that it can be transmitted over long distances.
So we required modulation to transmit the signal long distance.
So to resist noise interference or signals interference.
No, I think there is a gap in understanding in yours. So that's why I asked the question to verify. Modulation is not for strengthening the signal. Modulation, what does modulation do actually? It translates the frequency from one to the another. A band pass, like a voice is a low pass signal. If you modulate it, it becomes a band pass signal, right? Suppose you have a frequency between 0 and 4 kilohertz, your voice, and if you modulate with a carrier of 1 megahertz, then your signal spectrum will be that whatever the carrier frequency FC plus minus that 4 kilohertz. So it becomes a band pass signal. Okay, so it's not a low pass or a high pass signal, but a band pass signal, and you can choose the carrier frequencies for different persons or different programs, and therefore you can place them in different places in the spectrum, and therefore you can combine them and teach them that transmit them simultaneously through the same medium without any overlap, without any interference. Is it clear to you, Ananya?
Yes.
No, it is not strengthening. Strengthening is different. You can increase the power and the signal will become stronger. Modulation is that you, in the frequency domain, you are trying to separate them and transmit them simultaneously. And that means you do modulation and then after that you do frequency division multiplexing. So that's very fundamental. So you will see later on, whenever we consider any modulation scheme, we will also examine their spectrum. And every modulation doesn't have the similar bandwidth. Different bandwidth for different modulation schemes. That is also a very important thing. The second thing is that if you are going for radio communication, you want to transmit a signal. When you want to transmit a signal, you need an antenna. Right? The antenna size is also a very important thing. Antenna sizes are related to the wavelength of the transmitted signal. When you get a band pass signal after modulation centered around a very large carrier frequency, the corresponding wavelength becomes very small because lambda is equal to C by F, right? And therefore antenna size also become small, or it assumes a size which you can design and handle more easily, like microwave antenna, etc. So purpose of modulation is to shift the frequency or translate the frequency, they call it, so that you can multiplex, you can transmit more easily over a radio medium, or even you can, if you want to transmit a multiplex signal through a wired medium, then also it may be used, and so on. So with this brief conceptual introduction of modulation, now I want to say that as in analog communication systems, the modulation could be also for digital systems where the basic modulating signal is a digital signal, which could be binary or multi-level. And when you play with the amplitude of the carrier signal, then it becomes amplitude shift king. because it is not model. The people call it shift because you are digitally changing. So you shift from one value to the other value. So people more relevant way people express that is amplitude shift keying or ASK. People can also have phase shifting. That is called phase shift keying. I'll tell you how it is done. I will show you by diagrams how it is being done in such cases. And similarly, frequency shift keying. And one can also combine amplitude, one or two of them or three of them, and that leads to some combined modulation techniques. So they are variants. So now you can see the modulation can be of different types, and since the modulations are different types, demodulation could be also correspondingly different types. Now demodulation can be defined, can be carried out in two distinctly different ways. One is non-coherent demodulation, another is coherent demodulation. You must have studied amplitude modulation in analog communication system. And you must have studied what is called envelope detection, and also you have studied possibly the coherent demodulation. Do you have any idea about that, students? What is coherent and what is not coherent? Like let me help you that if you have an amplitude modulated signal, what happens actually, the envelope of the signal before modulation it becomes a constant DC, right? But when you do the amplitude modulation, amplitude varies with time. Amplitude varies with time, in accordance with the modulating signal. So if you pass it through a rectifier, like half wave rectifier or full wave rectifier, and then pass it through a low pass filter, you get the envelope of the signal. So in this kind of demodulation, you just get back your original modulating signal, okay, without knowing anything about the carrier. Because carrier has got a phase and a frequency. You don't worry much about that, and that is called non-coherent. But there are some techniques which is called coherent techniques, where you multiply the incoming signal by the a copy of the carrier signal. However, this carrier has to be same replica of the carrier that is used in the transmitter. If you multiply the amplitude modulated signal by a coherent carrier or sine wave, that is a cosine wave, and then again if you filter low pass filter, you will also get back the signal, the original modulating signal. So that is called coherent demodulation. Why it is called coherent? Because the carrier that you use in the receiver, that must be coherent in terms of phase and frequency. That is same as frequency and phase, that should be used for the demodulation. So there are some advantages of coherent demodulation techniques, right? But the coherent demodulation techniques, hardware is more complex, whereas non-coherent detection like envelope detection or demodulation is much simpler. But its performance is somewhat inferior to the coherent techniques. Interestingly, if you look at this, some modulation schemes must employ coherent demodulation, but others can have both options. For example, PSK family. PSK means phase modulation, phase shift keying. Now, phase shift keying, it will be binary phase shift keying, then MRE, multiple level phase shift keying. Because this information lies in the phase of the carrier, you must have a carrier which has a specific reference phase, which is basically the transmitter carrier phase. So for any PSK signal or any phase shift keying signal, you must use the coherent demodulation techniques, which we'll consider in much details later. But for ASK and FSK, I will show you that you can use either a coherent or not coherent. Of course, coherent will give you the better result at the cost of hardware complexity. And then we consider the noise. Whatever you are doing, modulation and demodulation, you will get back the signal, but at the same time there is a noise, as you must have studied in your analog communication systems. This noise will accompany the received signal and contaminate the received signal. I will show you how it does. And as a result, you will have a finite SNR. So finite because noise will not be zero, so the SNR, signal to noise ratio, will be finite. And because of the signal to noise ratio, finite signal to noise ratio, what will happen? Some of the bits, when you try to demodulate, basically you are trying to get back ones and zeros, right? For binary cases. Your modulating signal is like sequence of 1 0 1 0, which you have studied in your module 2, that binary baseband signal. So those ones and zeros you are going to retrieve. Now what will happen? Because of the noise, some of the bits will be in error, and the bit error rate, that means number of errors in a received bit stream divided by the total number of bits. That bit error rate, some people call it bit error ratio, some people call it bit error probability. They are one and the same. So bit error rate will be high, and you should know that bit error rate should be pretty low, pretty much low, to make a communication system reliable. Like a good number for bit error rate could be, 10 to the power minus 5, minus 4, like that. So, if you say that you have a bit error rate of 10 to the power minus 6, it means that one bit in a million, actually, in a million bit is going to be an error. It might sound a little bit absurd, but it is not really. In today's world, when you have digital communication, you are sending bits and bytes one after another, long files, long documents, and in a packet, it's basically packets of bits actually. Now, if a packet has got 1,000 or 10,000 bits actually, and then if you have a bit error rate of 10 to the power minus 4, that means in every packet there is going to be an error, and therefore every packet has to be retransmitted over and over again. So to make the system reliable, the bit error has to be much lower than that. And that's why I said a good bit error rate could be 10 to the minus 5, minus 6. In fact, what Professor Solanki told me about optical communication, there nobody talks about a bit error rate above 10 to the minus 9. People are now working with 10 to the minus 9, 10, minus 12, because there the bit rate is much higher. So number of bits going over the medium much higher as compared to the cable coaxial copper or the wireless medium. Okay, so bit error rate is a very important thing, and as you will see later on, for each and every modulation scheme, meticulously we will try to find out signal to noise, signal and noise, power, and bit error rate, and the spectrum. These are the three things which are going to define how good or bad is your system, your communication system. Right. Any question here from anybody? Okay. Yes. So if you go to the next item, this is called carrier synchronization. As I told you earlier, that can you see my cursor on the screen? Over there, sir?
No, sir. Your cursor is not.
My cursor is not visible, no?
No, it's not visible, sir.
Oh, how to make the cursor? If the cursor is visible, then it becomes still better. Okay, I'll see.
Slides are changing, but cursor we cannot see.
Anyway, I hope you can see that carrier synchronization.
Yeah, it's carrier synchronization clearly visible.
Carrier synchronization, as you know, for coherent demodulation, as I said, you need a copy of the carrier that has been used in the transmitter. A copy of the carrier means that it has to be coherent. Coherent means your phase and frequency should be synchronized with the phase and frequency of the transmitted carrier. This is not a small job. You must have a separate module in any receiver where the carrier is recovered from the incoming signal. You know why it is to be recovered? Because in receiver you can have another stable carrier, and with that you can carry out the remodulation process. But the idea is that you don't need the best possible carrier of the world, of the earth, to recover a signal. You require a carrier which is as good or as bad as the incoming carrier. If the transmitter carrier has some phase instability, your carrier should have the same instability. It should be in sync. That's why carrier synchronization. So actually this carrier should inherit, like a child from a parent. This carrier should inherit all the vice and virtue, right? All the vice and virtue of the carrier that is coming from the transmitter. As you know, when you design an oscillator and you generate a carrier waveform, that waveform will have some little bit of phase instability and frequency instability. exactly same instability has to be there in the receiver. Otherwise, it will not be sync and it will not be coherent. So therefore, the only way to ensure this is that you recover the carrier, you recover the carrier from the incoming signal itself, and which is not a very small job. We'll go through it and we'll see that how it can be recovered. And using that carrier, you have to demodulate. Okay, and then there are other synchronizations called bit and frame synchronization, the last bullet in this slide. So these subsystems would be necessary after the demodulation to retrieve your bits and words. So once you have demodulated the signal and you have got the baseband signal, you have got 1010 bits of ones and zeros, sequence of ones and zeros, and you have to, suppose there are five ones at a stretch, so you have to sample 5 times exactly at the same correct instant. So you therefore need a clock which is also a replica of the clock that is used in the transmitter. Again, this clock should be as good and as bad as the clock used in the transmitter. So yet it has to be recovered. Nothing like generating a local clock. You can have a very costly clock generator, but it will not really work for you. So therefore, for bit synchronization, you have to recover the clock. So this comes under the purview of bit synchronization. And once you have taken the proper decision about ones and zeros by sampling the baseband signal at proper instance of time, you also have to find out the border of a word, like frame. So because bits are coming in frames or words, so which is the starting point, which is the ending point, and that is what is called frame synchronization. And that has to be also done by using some clever techniques, which is called frame synchronization techniques. Okay, so these are the basic features or the salient features of the digital modulation demodulation techniques. And over the entire lecture on this topic, during all the lectures on this topic, we'll recall these issues again and again, over and over again. Now, I think I will consider this last slide for today's discussion. I have shown you the 3 basic digital modulation techniques. You can see the first one is ASK. So that means there was a carrier where you can see it has been modulated by a binary sequence 0, 1, 1, 0, 1, 0, 0, 1. So for 0, we have removed the signal completely. So amplitude has been shifted to 0. And for 1, there are 2 ones, consecutive ones, we have retained the carrier. So we have got continuous sine wave. Again for 0, we have chopped off the signal. So this is what is called amplitude shift keying. You can see clearly that if you take this signal, and pass it to an envelope detector, it will give you that 0, 1, 1, 1, because if you do pass it to an envelope detector, that's like a half wave rectifier or full wave rectifier, it will take the tips of the sine wave and therefore reproduce that baseband signal 0, 1, 1, 0, 1, 0, 0, 1. Okay, and if it is phase shift keying, it is actually the same sine wave, but at the bit boundary, when the baseband goes from 0 to 1 from the left side, you can see the phase of the sine wave suddenly changed by 180 degree. You can see that. If you look at the inset of the right hand side, you can see that it is a sine wave or cosine wave is basically a phasor which is rotating well and with a particular amplitude, with a particular frequency and with a particular instantaneous phase. Its projection on the real axis is the cosine and the projection on the vertical axis or the imaginary axis is the sine. So whatever it is, so the the real axis projection of this rotating phasor will have the information about the amplitude, phase or frequency which is switched at the beat transitions. So in the phase shift keying, I can see that the phasor is, you can see that 0 and then 1. First, right from the left, if you see, there is a 0 and then there is a 1. Between 0 and 1, at the boundary between 0 and 1, phasor makes a quick movement from the present position to the diametrical opposite position in 0 time. Okay, so in other words, the phasor makes a very fast movement from the present position to the diametrical opposite positions, implying thereby that it has gone through a phase shift of 180 degree, and that's why you see that the sine wave which ends at the bottom suddenly goes at the top. That is what is the 180 degree phase shift. However, such phase transitions do not take place between 1 and 1 because there is no boundary where the baseband signal changes, right? And then again 0 comes, or 0, 1, 1, 0, again 0 comes and again there is a phase shift. So this is how it goes on. So whenever there is a transition, for ASK you chop the signal, and whenever there is a phase shift keying, you just turn the phasor to the opposite direction, diametrically opposite position. And that is what is phase shift keying. Whereas for frequency shift keying, interestingly, it is not like that. It is just the frequency which is changed. You can see that for binary 0, frequency is slightly lower because time period is slightly wider, larger. And when it goes to 1, the frequency switches to a higher value. So we have got frequent transitions, right? So for 2 1s, you have got higher frequency. And then again the 0 comes, then you get a lower frequency and so on. So like frequency modulation, here also frequency is shifted between 2 values because it is binary frequency shift keying. And using this, you get FSK. I would encourage you to look at these 3 waveforms and try to discover that what is the fundamental difference between all these 3. You can see that for ASK, if I try to find out the average power, which will be lower than the peak power, because during the 1 transition the signal is present and during the 0 transmission signal is not present, right? So average power will be almost, if 0s and 1s are equally likely with probability of half, then average power will be half of the peak power. Whereas you can see if you look at the phase shift keying and the frequency shift keying, it's a constant envelope signal, it's called constant envelope. That means the envelope of the signal does not change. Whatever change takes place for the modulating signal is in terms of the frequency or the phase. So they are a constant envelope signal. Now the constant envelope signal has got certain merits in digital communication systems. We'll discuss about that in the next classes. So now with this we have an idea that these basic 3 modulation schemes. One is ASK, where the envelope, the power changes with time, instantaneous power, and average power is less than the peak power, whereas for a PSK and FSK, it's a constant envelope modulation. And we will see that we can combine amplitude shift keying and phase shift keying and so on and so forth. There are different varieties, and I will consider some of them which are there in your syllabus and talk about other things also in brief in my next classes. So Professor Upadhyay, I think this is the basic introduction of modulation techniques, and it may be a good time to talk for me.
Yeah.
My driver has also come to take me to the doctor.
No problem, sir. Almost you have completed the class, and with this introduction, I think we can conclude today's class, and we'll meet again on Thursday. Okay, thank you, sir.
Yeah, and students can any questions also if they want.
And we are expecting, students, we are expecting that you all will ask the questions from the sir whenever you find any doubt, or whenever you actually study something in your book. Then if you have any doubt, you can ask the questions to the sir. Don't hesitate and don't waste this precious time, right? So you please all try to utilize this time.
Okay, even though you are having some doubts, you can ask in next class because sir is in hurry. So you please go through the basics what sir has taught, and in next class also you can clear your basics. Okay.
They have the copy of my slides, right? Through this, they can see my slides through this.
It is uploaded, sir.
So no, do I have to upload?
Yeah, if you upload, then only it will
I
be there.
I opened today the MS Team. I saw my thing is already there. My slides.
No problem, sir. If you could mail us, then also, we can also upload in the team.
Excuse me, sir. It is already uploaded, sir.
Okay, fine. Yeah, it is there. I think somebody has told that it is there. Okay, fine.
Questions and whatever. Okay.
Okay, sir. So I think we can conclude today's discussion.
Sure. Yeah.
Oh, okay. Thank you, sir.
Thank you, sir.
Okay. Thank you.
So now you can leave, students. You can leave, and please join on Thursday for other class. Thank you.
Thank you, sir.
Thank you.
Sir, I think you can only